ME3210 Project 1 recording, and I'm Ryan Mack. This presentation will discuss 5 topics which could be tools, techniques, strategies, models, or processes that will aid in the development of a better engineer. And these 5 topics may originate from textbooks, slides, lectures, and videos covered in class. And this video will be no more than 10 minutes long. The first thing we'll talk about is design for manufacturing. So what is it? Design for manufacturing, or DFM, is the process of designing products so that they are easy and cost effective to manufacture. It focuses on simplifying product geometry, reducing part count, and selecting processes and materials that optimize production. This prevents over-engineering and encourages consideration for the ease of manufacturing. It also reduces waste and the need to rework. It is important to design things for manufacturing because not everything that we create digitally can be easily manufactured, and by thinking about how things can be manufactured, we can reduce costs and ensure that our products can actually be brought into real life. So applications. It is used in almost all aspects of engineering anytime when manufacturing is involved, regardless of if it is mass produced or produced on a one-off basis for a specific project, as without designing for manufacturing, it would be next to impossible to manufacture. So why is this important? Because if you don't design for manufacturing, then the product might simply not be able to be manufactured easily or at all. Designing for manufacturing properly will result in lower production costs and complexity, which helps down the road because it could help in making the product easier to fix and repair. It ensures better coordination between design and manufacturing teams, so the design team does not spend lots of time designing something that cannot be brought into real life, and doing so will also reduce the time to market required for a product. Limitations include the fact that design for manufacturing is limited to current design methods, so it is not very future looking in terms of what types of methods you could use to manufacture your product. And some things can be very difficult to manufacture, so by designing to manufacture, there might be some design limitations, and this can also result in some less aesthetically pleasing designs. And by doing so, we also limit material or geometry choices, so this might not be ideal in some cases. The next thing we'll talk about is failure modes and effects analysis, or FMEA. This is a matrix used for identifying potential failure modes, determining the risks each failure causes, prioritizing actions to reduce risk. It is typically done by tabulating all of the failure modes and assessing the severity of each, weighing it against the probability of occurring, so that designers can focus on the most critical needs. Almost all design should use an FMEA, as preventing product failure is far easier than trying to fix things after the fact retroactively, and it is used in planning frequently to identify key points of focus for design. It is very important because proactive approaches to risk mitigation means failure is less likely to occur down the road, which increases reliability and safety of products. It anticipates failures, and designing to prevent them is far less costly than letting them happen and trying to fix them after. In some cases, it might even be impossible. Limitations of FMEA include the fact that it is only as good as the person who created it, as the creator of the FMEA might overlook some failure modes, meaning the FMEA is not as useful as it could be. Conducting an analysis is time consuming, and it requires a solid knowledge of the product to do so. The product lifecycle analysis is the next thing we will talk about. So what is it? The product lifecycle analysis is the process of identifying all the stages of product goes through, from concept to manufacturing to use and disposal. Considering the product life cycle allows designers to think about future uses of the product and potential issues down the road. It is used particularly in the conceptualization of new products and is important in eco-friendly design and product upgrade considerations. It is important because it encourages designers to be more forward-thinking and think about uses of the product in the long term, allow for better planning for future upgrades to the product, and reduces the environmental impact of products. Limitations include the fact that it is difficult to predict the entire life cycle and it requires extensive cross-functional planning. Number 4 is CAD, or computer-aided design. So this is a form of software used to create models of objects in a computer, and it's used often for prototyping, manufacturing, and testing. It is used in all aspects of design and engineering because it is usually necessary to first create a digital model of a product to run analyses on it and perform iterations before creating a prototype, as CAD is practically free, but creating a prototype will incur material costs. It is very important because it is often infeasible to create a prototype without anything to work off of, and allows for a reference point to manufacture items from. CAD also works with tools like 3D printers and CNC machines to allow for easy manufacturing, and it makes design iterations much faster and allows for collaboration. CAD models are also very easy to modify and update. Limitations include the fact that it is quite difficult to learn how to use, and it is purely theoretical, so some unmanufacturable designs can still be created in CAD. So the user who creates the CAD models needs to be aware of this and avoid using that in CAD. This could be combined with the design for manufacturing principles to make it more useful. CAD models also do not guarantee good design or outcomes, and what works in CAD might not work in real life, so there is something to be aware of. This includes practical considerations like gravity, floating parts, and things like that. FEA, finite element analysis, is the fifth and final thing we'll be talking about. So what is this? This is a numerical method used to analyze physical effects on an object. And this includes forces, stresses, vibrations, heat transfers, fluid flows, and so on. It works by breaking down an object into many small parts using a mesh and doing analysis on each of those components. It is used in all situations where modeling of real-world scenarios is needed prior to manufacturing for safety and performance validation without actually having to perform the stresses on the real object itself. It is important because it is the only way you can visualize the effects on product design without actually needing to produce a prototype, and it also works with CAD to allow for easy updates and changes to the model based on FEA results, and it is also useful in identifying weak points early to optimize the material use. Limited by the computing power provided, so as FEA can be very computationally intensive, so this is something to be aware of. And it also requires very accurate material and physical properties to be done correctly. And here are the sources. And that is the end of the presentation.